Well, hello again, everyone. Thank you so much for joining us for another L3 Levine Electronics and Electrics webinar. We are so happy today to have Terry Smith of GE Multilin present to us. I think many of you know Terry. Terry's been in this business a long time and understands the art of protective relaying. A couple of housekeeping items before we get started. There are some buttons, I think to the left of your screen. You can ask questions. There's a handout on the left that is a copy of this presentation for your later reference. Your microphones are muted, but that doesn't mean we don't want to hear from you. Please ask questions, whether in the chat box or the question box, and we would love to answer them. Without further ado, I'm going to turn it over to Terry Smith of GE Multilin.
All right. Thank you, Mac. Thank you guys for attending. And hopefully today we'll all leave here a little bit more knowledgeable about high impedance bus protection. So one of the few things that John Levine does right on these webinars is that he likes to do these poll questions to keep you guys involved, right? Because I know we're all getting webinar fatigue. It's like the 24th month of 2020. And we've been to 1 billion webinars by now, and sometimes they're boring, right? And to keep it a little less boring, what John likes to do is he likes to do these poll questions. So let's go to the first poll question. And the first poll question is, what is high impedance differential? Is it a mechanism to provide differential protection with a resistor across CT outputs? B, a mechanism to detect high impedance faults on distribution circuits. Or C, they are the same thing. And there's a way somewhere for me to see what the results of the poll are, but I can't remember how to do that right now. So
just drop down your poll.
Oh wait, I can see it now. Oh, we're hitting it 50-50. They're the same. Okay. Okay, that's like 30 seconds. That's long enough. Oh no, we've only got 24% have voted. So let's give it a couple of seconds longer so that people can figure out how to vote. We're almost at 40. We're much higher than the percentage of voting in the United States general election at 60% right now. That's great. We still got 32%. 32% of these guys that are scratching their head trying to make up their mind.
All right, I'm closing it. You want to share?
All right.
You want to share?
Yeah.
We'll share it.
Okay. Do I have to share it? How to do that?
I did.
Okay. So 44% of you were right. What high impedance differential protection is, or high impedance bus protection, which is high impedance differential. It's basically a mechanism to provide differential protection with a resistor across the CT output. One of the ways that I like to sort of think about this is that high impedance bus protection makes use of the fact that CTs can saturate by forcing them to saturate with a resistor across the CT output. And by forcing them to saturate, we get much more predictable performance. And based on that predictable performance, we can provide protection. Now, option B there was a totally separate thing. And option B basically is a different thing. It applies to the distribution system. And this is where we use particular algorithms that are going to identify particular waveforms and particular energy in those waveforms to detect a high impedance fault on a distribution circuit. Now, that is getting a lot of attention right now, that particular type of fault, and detecting that type of fault, because of the fires that we had in Australia earlier this year, and also the fires that we had in a year or so ago out in California. And both of those might have been caused by high impedance faults like this. But our presentation today is around differential protection. So we're going to protect buses with differential protection with a resistor across the CT outputs, right? Okay, John, are they seeing my screen again?
They should be, yes.
All right. So let's jump into this and talk about what this is. So this is basically what this sort of protection would look like. And we're going to take a
You're seeing the
protective
pole.
relay.
There it goes.
Yeah. This is basically what this would basically look like. We're seeing a protective relay, which in this case, I've shown the UR relay here, and a high impedance module. So what I'm showing here, this HID that's right above it. So the HID right here is a high impedance module. Now, if we were looking into that module, the main thing that's in there is a resistor, right? And it's a 2,000 ohm resistor. And so basically what we're going to do is we're going to take all the CTs like we show on this bus with a lot of circuit breakers on it. And we're essentially summing all of these CTs together. So we're only showing a single phase. You do this on all three phases. But what you see here, where I'm circling these two wires, what is going to that HID module should only be the vector sum of all the currents connected to that bus. And so what ends up happening is that we have, right now it's showing a fault on the bus, right? So if we have a fault on the bus, we're going to have current flowing into the bus and into the bus. Now, we may have some current flowing out depending on the level of this fault. If it's a real strong fault, we probably won't have any current coming out. And so if that's the case, we got current flowing in here, we got current flowing in here, and very little current flowing out, we'll see current going into that HID module. Now, the challenge with all bus protection is we want to trip fast, but we don't want to lose the whole shooting match. We don't want to lose the whole plant. We don't want to lose the whole substation for a misoperation. So it not only needs to be very, very fast, but it needs to be very secure. And so the way that you get security here is if you have a through fault or you have an external fault, like a fault where I just drew this X, what I would expect to see is I would expect to see current flowing into the bus, and I would see current flowing out, right? Now that current flowing out should equal the current flowing in. So what we should see flowing into the HID module is no current. So there's zero current. So inside that HID module, there is this 2,000 ohm resistor. There are some other things in there that serve to protect the 2,000 ohm resistor and protect the HID module. We'll talk about what those things are a little bit later. But right now, the main thing that we really need to talk about is how this works. Now, I said earlier that the way this works is this makes use, this high impedance differential scheme makes use of the fact that you can saturate a CT, right, by forcing the CT to saturate. And because it's going to saturate, we can get very predictable performance. Now, what I show here, so over here on the far left is my bus. So this here is the bus that I'm protecting, right? There's my bus that I'm protecting. And in reality, the differential zone that I'm protecting, let me get rid of that. The differential zone that I'm protecting is from this CT right here down to this CT right here. Now, for the sake of simplicity at this moment, I am just showing a bus with 2 breakers connected to it. There could be one of the nice things about a high impedance differential scheme is that there can be a lot of breakers connected to this bus. So to understand high impedance differential, we sort of need to understand what is happening on the CT. So what I've shown is these 2 CTs, the equivalent circuit of them, and how they're wired external and how they're connected to the HID module, right? So this is my HID module here. I'm connected here and here. So the first scenario that we should talk about is let's keep the thing from not operating when it's not supposed to. So in that case, if I have a fault out here, that is outside of this differential zone of protection. So I should have current flowing here, right? So that's flowing in here, right? And that means it's flowing out here. Now, down here, that current's flowing in this direction, right? That means it's flowing in here. It means it's flowing out the dot here because the dot's away from the protected zone. That means it's flowing here, right? Which means it's flowing in here, which means it's coming in this direction, right? Now, what ends up happening here is this current is going to basically circulate here, this secondary current. It's going to circulate in the secondary of the CT. Now, the reason it's going to circulate in the secondary of the CT is because this 2000 ohm resistor, so remember, sitting inside of this thing is a 2000 ohm resistor. So the reason it's going to circulate in those secondary currents and not go through the HID module is because that 2000 ohm resistor is a lot larger impedance to the impedance of the CT circuit. So this is a very small, the CT circuit here is a very small impedance compared to that 2000 ohm resistor. So nearly all the current is going to flow in this direction. So that's what the thing does for a external fault. So let's change our minds now and let's change our fault location, right? So let me get rid of all my drawings here or all my scratch marks. All right. You can't draw a circle around stuff. You can't hold your, there we go. Okay, so let's take a different scenario now. Let's say, what happens if we have an internal fault? Now, there's a couple things going on there, right? First thing that's going on is that fault current, it depends, right? So if there's a source up here and a source up here, then we've got current flowing into the fault in this direction. We got current flowing into the fault in that direction. So that looks like current flowing into the dot here, right? It's flowing here. We got current flowing into the dot here, and it's flowing here. So since the current is flowing in this direction, at this summation point here, it's going to go in this direction, right? And in reality, it's going in that direction because since I'm forcing current into the CT secondary here, since I'm forcing that current there, that impedance of the CT circuit looks a lot larger than the actual 2000 ohm resistor here. So in that case, we're going to have current flowing through the resistor here, and then it's going to flow back up here and here, right? So we'll have current flowing through that resistor. Now, the current that flows through that resistor will vary because, or it's going to be unique because that 2000 ohm resistor is going to cause these CTs to saturate. So it'll be a smaller current that's flowing. It won't be the 10, 15, 20 amps of secondary ground fault current that we expect because we're going to force that CT to saturate. It'll be a much smaller value. Now, another scenario is what happens if I don't have a source down here, right? I don't have a source down here. Oh, my currents look more like that. So if that's the case, let me draw this back in. So now I've got current flowing into here. There's no source here, so there's no current flowing out there. Got current flowing into the CT, and it flows in here. Now, since there's no current flowing here, this looks like a high impedance compared to the 2,000 ohm resistor. So now we're again going to have current flowing through the HID module back into the secondary. So we'll have current flowing in there. Now, what I haven't drawn here in this scenario, I haven't actually drawn the relay that's going to do the trick. So if we go back here, I did that for simplicity reasons. That relay is actually on where it's connected in series with that HID module. So in reality, the relay would be sitting right here, and it would be measuring current through it. There's two ways to do this. The electromechanical PVD relay, it would measure the voltage across that 2,000 ohm resistor, and that voltage would be its operating quantity. If we're doing this with a now obsolete GE-MIB relay or a modern microprocessor-based relay like this, connected to an HID, if we're doing it like that, or the MIB, we're actually operating from the current that's flowing through the relay. And again, this will be a fairly small current in secondary terms. So let's take a look at how we actually calculate that current, what that current should be, and how we set pickup for this. Because this scenario is the calculations are fairly simple. And there's just one pickup setting, right? There's the pickup for this overcurrent, this instantaneous overcurrent that's going to be tied to the currents for that are in series with the current inputs on the relay. They're in series with the HID module. So when we do calculations, there's really two calculations we need to do. And so these calculations I'm going to take you through, you can find these calculations and examples of these calculations in the PVD manual. You can also find them in the MIB manual and the HID manual. And so basically what the calculations are is there is a minimum pickup calculation and a sensitivity calculation. So the minimum pickup calculation is really determining what I should set my minimum pickup at, right? And actually it's a little confusing because this is we're calling it minimum pickup, but this is really, I need to set it at least lower than this, right? So let's talk about the minimum pickup calculation first. So this is the equation for the minimum pickup, right? So if we look at what this equation is, we're taking this first term here, this 1.6, and the 1.6 is there because we're using that to accommodate the fact that we can have DC offset when we first strike the fault. So when we first strike a fault, we know we'll have DC offset. That means the peak of the current may be up to 1.6 times the peak that it normally is. That'll cause us some problems if we don't accommodate it. So that's what that 1.6 there is. A CT performance factor is basically a derating factor that we're going to calculate in the next slide or slide after next. And basically that K factor is a derating factor based on the CT performance. So RS here, that is the lead resistance. And, RL is the lead resistance. RS is the secondary winding resistance of the CT. The IS here, that's the fault current. The N is the turns ratio of the CT. And then the 2000 is there because that is the size of the resistor. So what we're doing here is we're taking a couple of rating factors, this 1.6 and K, and then we're taking this combined lead or this combined secondary resistance here, and we're dividing it to get by the N. We're taking the fault current, dividing it by N to get the secondary fault current. So if we take IF, that fault current in secondary terms, multiply it by a resistance, we're getting a voltage. And that's the voltage that's going to appear across that 2000 ohm resistor. So when we divide that by that 2000 ohms there, that 2000, that will give us a current. And that is a sort of a minimum pickup current. So to sort of solidify that, let's make some assumptions. Let's assume we're doing this for a medium voltage switchgear. And we're going to use a CT, which is an ITI model number 561-202. So I'll show the knee point voltage in a few moments, but the knee point voltage of this particular CT, and this is a 2000 to 5 CT, knee point voltage is 125 volts. And it has the secondary winding resistance of 1.021 ohms. It's a C100. It's 2005 C100. Now, this particular, all these numbers that I just quoted you, they come from the CT catalog number for that particular CT, this ITI 561-202. Now, I'm going to assume a cable resistance for my longest run of 0.5 ohms. So this looks like this is maybe 500 feet away, which is not too untypical in a transmission bus, but might be a little extreme for a switchgear. But nonetheless, I've calculated my cable resistance of 0.5 ohms. And the next thing I really need to know is I need to know my fault current. Now, in this particular case, the PVD manual talks about what you can do. So the best thing to do is to know your actual fault current and use your actual fault current in your calculation. Now, if you don't know your actual fault current, the other option you can use is the current, your fault current will be less than the breaker rating. So you could set it to the breaker rating, the breaker interrupting rating. In this case, these particular breakers, they're rated to interrupt 65 kA, which is probably a lot more than you have, a lot more fault current than you have available in this particular system. But since I don't have good information, that's what I've essentially got to do. So the first thing I need to do in this minimum pickup calculation is to calculate a performance factor. And then based on that performance factor, I can get to a derating factor. Now, the performance factor, it's that same term, this RS plus RL. So that's the lead resistance and the secondary winding resistance times the fault current. Then we're going to get it in secondary terms by dividing it by the turns ratio. And then we're going to divide that by the knee point voltage. In this case, that's actually, I said that was 125. I'm showing 150 here. It's not going to matter. It's not going to matter. But that should be 125. So that gives us a performance factor of 2.189. Now, to get to the derating factor, we use a K-factor graph. Now, this graph comes from the PVD manual, and the MIB manual, and the HID manual. So 2.189, here's this equation here. So it's 2.89, it's somewhere up in here. So that gives me a performance factor of 0.7. So I should expect this, that's what I need to use for my performance factor and my minimum pickup calculation, 0.7. So let's see what my minimum pickup calculation is. So this is the equation we were talking about earlier. I've got all these values now. So it's 2. This P here is 2 because it's there and back for the leads. So lead resistance is 0.5. Secondary winding resistance is 1.02. There's that K factor I just got from the graph. It's 0.7. And here's my 1.6 to accommodate the DC offset. CT ratio, remember that's 2,000 to 5. That gives me a turns ratio of 400, which is that term there. There's my 2,000 ohm resistor, and then here's my massive 65 Ka of fault current. Now, when I do all that, that gives me a pickup value of 183 milliamps. So even though this is called a pickup, it is a sort of a maximum pickup value because if I were using a smaller fault current, which my fault current absolutely has to be smaller than 65 Ka, otherwise I'm overduting the breaker, then this 183 milliamps is going to be smaller. So even though we're calling it a minimum pickup, it's sort of a maximum pickup. It's what I do not want to set this above. If I set my fault current bigger than this, I may not operate. So I want to set it below that value. Then my next calculation that I want to see is how sensitive I am at that pickup value. Right? So that is a sensitivity calculation. And that's the next calculation I need to do. So this is the Imin. So that is the minimum internal fault current that I would trip at. So this is going to tell me what is, for that pickup setting, what's the minimum fault current I'm going to trip at. So this would tell us where we want to go down to. So if I set this down lower than 183 milliamps, this is going to tell me how much of a fault I can actually see. So I want to see what I can see with this 183 milliamps. So I use this, so I have to do this for each of the breakers on the bus, and that's what this 1 to N here is. So I'm in as minimum internal fault current. This N here is the CT ratio. The N here is the number of breakers connected to the bus. The I1 is the current in the MOV. So in addition to that 2,000 ohm resistor, there's also an MOV, a thyroid MOV. Guys, I'm back. John, can you hear me?
Yes, we can hear you now.
Okay, guys, I'm sorry. There was a huge lightning strike just right outside my home, just right now. And as soon as that happened, my internet went away. So apparently I'm back. That's great. What was the last thing you guys heard, John?
We're showing your calculations of sensitivity.
You weren't paying attention. You don't remember what the last thing you heard were.
I'm looking at the last
That's
slide.
Okay. Okay. So you're seeing this minimal sensitivity. Okay. So I1, that's the current through the MOV. I think you heard me through that. IR is the current through the MIB to pick the relay. So that's the pickup setting. And this I here, what this I right here is the secondary excitation current of the CT at the voltage equal to the 87L pickup, right? So we just calculated that 87L pickup at 0.183 amps, right? And so that would be times the 2,000 ohm resistor. That would be a voltage of 366 volts. So what we need to do at this point is we need to look at the excitation curve for this particular CT, and that will tell us what the current is, the secondary excitation current at that voltage. So remember the voltage I just calculated was 366 volts. Now this is the 2005 C100 right here, this top curve right here. So here's 100 volts, there's 200 volts, and there's 300 volts. So about halfway through that is 366. Well, for 10, that's a straight line. At any rate, that voltage that we would need to develop is greater than the knee point voltage. So what that tells us is that we cannot use this particular CT in this application. The reason we can't use that is because the CT won't develop enough voltage to support the application and support the current. So let's look at the mitigation factors that we could use here. On this example, there's a couple of things we could do to mitigate this. One of the things that we could do to mitigate this is we could try to use a lower setting. That lower setting is would have to be based on actual fault current rather than breaker interrupted current. That'll give us a lower setting. So that's probably not going to work. And the reason it's not going to work is because we're never going to be able to develop enough voltage across that particular CT. So one of the things that we want to think about is we probably never want to set the pickup of the high impedance module. We never really want to set that less than about 50 milliamps. And the reason we don't want milliamps is because these CT circuits will largely look like antennas, and they can get a lot of noise on them. And 50 milliamps of noise on that CT circuit and operates. So we probably, typically, when you do these calculations, the setting ends up being about 75 milliamps. But if we have, 50 milliamps, we multiply that times the 2,000, that's right at 100 volts. If we end up with a setting that's more realistic of 75 milliamps, so that'd be 0.075 times that 2,000 ohm resistor, that's about 150 volts. Now, in this case, this thing probably, it's gonna support about 200 volts. The knee point's here a little bit over that 150 volts. So we might be able to use that here with some caution, right? If we set it around 75 milliamps. So this brings us to our next poll question. So John, you want to open the poll? You want to open the poll? And the poll question is, when can I use a C100 in bus differential? And choices are almost never, never, and seldom. And nobody's answering the poll questions. They must have all dropped off when my audio went dead.
No, actually, you gained people during that time.
What?
You gained people. But you have more people now than
okay. Yeah.
I guess they're done with lunch.
So the poll's open, guys. Yeah.
Oh, y'all were doing so good. Everybody got it right to a point.
Open. Yeah. Oh, okay. Never, seldom, almost never. In reality, any of those questions or any of those answers are good, right? And again, the reason I say it's very difficult to use this C100 is because typically when I think about a C100, I think it's going to support a little bit over 100 volts, right? And so if I go back to this excitation curve, it supports this knee point is probably about 180 or so. Well, I guess this is a logarithmic still. It's probably about 160. So it supports a little bit over that. And so really and truly, I probably want to use at least a C200 on a. Let's see my screen again, John.
No, for some reason it hadn't popped back to your screen. Still showing
Okay.
question.
Let me share again.
Oh, there you
Okay.
go. We see it.
You seeing
Good.
my screen now, John? Okay. Yeah. Yeah. So typically, you're going to have to use at least a C200 to do this sort of high impedance bus protection. So that's one of the other downsides to this high impedance bus protection is the fact that it does require a C200. And you don't always have enough real estate inside of especially a medium voltage switchgear to put a C200. And it's got to be a dedicated CT. So this CT can't be used for overcurrents as well, feeder protection. It can't be used for feeder protection also because you're summing all these CTs together and putting a 2,000 ohm resistor across it. So that's going to be a problematic. So you need at least a C200, and you may not have room for a C200 or real estate. So let's talk about this high impedance module, what's inside of this thing. So I've already said there's a resistor in there. So there's a resistor, the 2,000 ohm resistor. So there's my 2,000 ohm resistor. And that resistor is going to pass some current. And the thing we know about resistors is they're going to generate heat. They're basically heaters. They're a resistor. So we need to be able to protect that resistor. So there are two things that protect that resistor. There is a MOV. So this here, pretend that's an MOV. The other thing that protects that resistor is some bypass contacts. And these are those bypass contacts here. Yeah, there's a really bad electrical storm outside. I may lose you guys again, but bear with me if you do. So the way this thing works is this is the vector sum of the current. So this is all those CTs brought together, and they're wired in here. And then here's the return for all those CTs wired together. And so here's my 2,000 ohm resistor. That's shown by this thing, my MOV, and my output contacts. Now, the way this is, the resistor, under steady state normal conditions, it should have almost zero current on it. And so it has a watt rating. We'll talk about that in the next slide. It's not a very large watt rating. So because it doesn't need to be, because under steady state conditions, you expect zero current flowing into this device. It is a resistor. The MOV exists to shunt the voltage if you have, or shunt that voltage, shunt that current if you have a large voltage that appears across the resistor, larger than it should have. That protects the resistor. The output, or the contacts that are shown here, those are tied to the lockout relay that is integral to the HID module. And what that lockout relay does is basically when you trip for your differential, not only should you trip a lockout that trips the breakers, but you also trip a lockout in the HID module, which will close that contact, which bypasses the current through the resistor. So, output of the resistor here, it's coming down and it's wired to input on the protective relay. The outputs of your protective relay, they should trip an 86, which trips the breakers. Also should trip 86 on the HID to protect the 2,000 ohm resistor. Now, the type of relay that you put here, you've got several options. So one of the options that you have is to use, so we no longer manufacture the MIB. So the MIB was a high impedance relay that had the HID module integral to the relay. Now you have to buy the HID and a relay. So some of your options on the relays are, you could use a 350 relay. So our 350 relay, if you do that, to get the currents to set down low enough, you have to buy a 1 amp input on the 350, a 1 amp CT input. The downfall to this one is it's not going to be as fast as the MIB, because the 350 is a much more cost-effective relay. Other option you have is a UR or an 850. Most people would use an 850. And those will have the same speeds or better speeds than the MIBs. The only thing there, and you can use a 5 amp current input, the only thing that I would caution there is that you have to set the current cutoff to a lower value so that it will operate from the 75 milliamps or so that the thing is going to see. So what happens if I wire incorrectly, right? Well, let's talk about this resistor. This resistor is 2,000 ohms. It's got a 75 watt rating. So if I want to see what current destroys this resistor, so I squared R is the power. So if I take the square root of the 75 watts and divide that by the resistance, which is 2,000 ohms, that means the rating of that resistor is 193 milliamps. So if you pass more than 193 milliamps through that resistor, you will destroy the resistor. It's not meant to have any current flowing through it, or hardly current to the steady state. 100 milliamps is 20 watts. That's a lot of heat. And so to put this into perspective, more than once, on more than one occasion, I've seen where customers, here's my breaker, here's my breaker, here's my breaker, and so on and so forth. And the way this should be wired is this guy should be connected to here, and this guy should be connected to here, and so forth and so on, right? Now, what could happen, or what has happened, like I said, more than once, is if here's my bus sitting up here, 10 other dots connecting the bus, and I've got a CT sitting here, and what's happened more than once is that this CT got rolled, right? So when that CT gets rolled, you've got current going to those resistors in the steady state. So what's happened, like I said, more than once, the switchgear, the system arrived in the field, they picked up a load and immediately started a big motor and immediately tripped. So what they decided settings. And in each of these instances, they increased settings until they got the thing to stop tripping. Well, like I said, 193 milliamps is the point where you start to destroy the resistor. You're at the 75 watts that the resistor is rated for. And even at 100 milliamps, you're dissipating 20 watts of heat. 20 watts is a lot of heat inside of this small enclosed space. So 20 watts, good news is it won't destroy the resistors, but it is going to generate a lot of heat. It's indicative of a problem with your wiring. You're never going to operate correctly wired backwards. So the other problem another problem with the high impedance bus protection is when you identify that you've got a CT wired backwards. You're seeing 100 amps flowing in the steady state through your resistors. You can't put your hand on the HID module because it's dissipating 20 watts of heat continuously. There's no forensics to really help you determine which set of CTs is rolled backwards, because all you've got coming into the relay, even if it's a microprocessor-based relay, is this summation of the relay currents. And because of that, you've got to do a lot of hard work, mainly by trial and error, to figure out which one of these CTs is wired backwards. And to make matters worse, a lot of people use low impedance bus protection in that today, and sometimes there's two cases where you fall back to high impedance. One of those cases is because that's just your standard. That's what you know. That's what you've always done. You're going to use high impedance rather than low impedance. The other case is you've chosen high impedance because you have a very large bus. Now, there's ways that we can protect large buses with low impedance bus relays, but sometimes they can become costly because you might need 3 relays. And so because of that, the low impedance becomes a much more economical, or a more economical solution. And in those cases, if you've got a large bus, you've got a lot of work to find the backwards CT by trial and error, which is, that's a tough problem to solve. So, in conclusion, getting towards the top of the hour, in conclusion, I'll say the high impedance differential has been around a long time. It's effective, but it does have certain downfalls. One of those downfalls is it requires dedicated CTs. These CTs cannot be reused for other things. They have to be dedicated to this high impedance bus differential scheme. All the CTs really need to be the same accuracy class and the same ratio. The CTs probably need to be better than C100s. And the last thing is you really don't get any forensics. You don't really get any forensics around how to solve a mis-op problem. All you know is your current that you've got there. So if you've got a wiring problem, it's very difficult to figure out which one of those CTs is wired backwards. So, John, do you want to remind them how to ask questions?
Yeah, if they want to ask a question, they can just type it into the question or chat box, and we should see it. Well, questions to come in. Terry, I actually had a case where a customer was rocking and rolling along with a high impedance bus differential at a paper mill. And one day they had a fault that was actually external to the bus. And sure enough, it tripped the bus relay.
Yeah.
And the reason it did, obviously, was one of the CTs was wired backwards. Problem is they had no way to know how to find where the CT was, which CT was bad. So they had to spend a lot of time trying to figure that out. Just so everybody's aware, Terry Smith and I both prefer low bus differential, low impedance bus differential. The problem is you got to bring all the CTs individually back. But we can do oscillographies, we can see waveforms, we can see exactly where the fault is and what occurred on it. I can also use different size CTs. We've got one customer that we actually went back and using all the existing CTs, we were able to add bus differential to a low impedance bus differential scheme. And we used the same CTs that were already there. So I can mix 300 with 800 amp CTs or whatever you need. So it's really, really nice. And all these fancy calculations he had to go through for high impedance that he's showing right now, we didn't have to deal with any of that. Okay.
So one of the questions that came in is what is this P term right here? So that P term is basically the number of leads. So that's going to be 2, there and back. So that's 2. And in my calculations, I think that's what I use. Yep, there we go. There's my 2. P is for method. But it actually means the leads there and back.
Terry, is there any kind of guideline on if I've got a bunch of CTs when I just keep paralleling them to the next one and the next one, and when I need to bring them all back in parallel?
So one of the things that you should try to do is keep. You might have what I often see on this, like in a switch yard, is there is a paralleling cabinet. So they bring all the CTs to that paralleling cabinet, and then that way they only have to run 2 wires into the relay house. If this is in switch yards, 2 wires to a relay house to the relay. So there is some place where you need to make up all of those CT circuits into a summation. Now, one of the guidelines that they always say is you try to keep the leads for all of the CTs about the same. So that's one of the reasons that in a switch yard, you might have this paralleling cabinet. So, let's say you've got a ring bus, or I don't know, let's say you've got a bus like this. So the breakers are coming off the bus some way like this. And your switch house is sitting over here. Typically what they would do is they put that paralleling cabinet right here. Well, they put it sort of in the middle. That way, all the CTs, they're not the same lead length, but they're more common than if you had to run. They're closer to the same than if you put it on one end or the other, and then you run back here. So that is one of the, that's one of the recommendations. There are some mechanisms that you need to account for. Also, when you do this, if you use multi-ratio CTs and you don't use the full tap, because a large voltage can appear across that unused portion of the CT. There's even some mechanisms where you can use, unequal CT ratios. Like I said, I don't recommend that. That's not a good idea. Thank you for your question, John.
Yep. Thanks very much.
Okay. Okay. Either my screen's locked up or I'm not seeing any more questions.
There was a statement from one person that said the CT backwards is a checkout issue, which I agree with. There are ways to check out a high Z scheme to ensure CT polarity is correct using current injection. It's tedious and takes a while, but it's certainly worthwhile. And I agreed 100% with that. But then I also told him how easy it is with low bus differential. I can just look at the waveforms and in 5 seconds tell you one of the CTs is wired backwards.
That's true. That's true.
You get a lot more information if you go with low impedance bus differential.
Yep.
Well, if nobody else has any more questions, we'll let you all go 5 minutes early. Thank you for attending. And we will be having more seminars this week. Tomorrow, what day is today? Today's Thursday. Yes. Tomorrow, Michael McClellan is presenting a simpler way to achieve accurate position control without using a servo drive, using one of our Danfoss variable frequency drives. Thanks, everybody. Be safe out there. Thanks, Terry.
You bet.